Given that you've clicked on this video, you probably already know that the Putnam test is one of the hardest undergraduate maths tests in the world. Every year students in North America gather to cry in exam halls all around the continent while attempting its plethora of challenging questions. Last year's Putnam was no different. Of the 3,415 students that attempted the paper, the majority scored less than 1 mark out of 120. Today, I'm going to cover question 3 from section B from last year's Putnam. But instead of jumping right into the solution, we'll approach the problem from the ground up. It's all to do with colour and numbers. The problem itself specifies the positive real numbers, but to get a feel for the problem, we will start by looking at the integers. We'll start by listing some of the integers, colouring them randomly out of a choice of 2 colours. The choice of the 2 colours is arbitrary, but we'll stick to the ones used by the Putnam, namely red and blue. We're interested in the set of all possible distances between 2 points of the same colour. Let's call this set D. We're going to use this set to recolour the numbers. Every number that is an element of D will colour red, and every number not in D will colour blue. What the question is asking then is if we repeat this process of finding the set D and recolouring the numbers over and over again, will all the numbers end up red in a finite number of iterations? It can be useful to start with a simple case, which for this question would be just the numbers 1 and 2. There are 4 possible initial states for this case, either both are the same colour, or they're the opposite colour to each other. The first thing to note is that we have a trivial case. When both 1 and 2 are coloured red, the system is already in a desired state. Therefore, it took a total of 0 iterations of the process to reach that state. Meaning the answer to the question here is yes, we can get to the final state in a finite number of steps. Now let's work out the set D for each non-trivial initial condition. When both 1 and 2 are coloured blue, the distance between them, i.e. 1, will be added to the set D. Meaning when we recolour the numbers, 1 will be coloured red and 2 will be coloured blue. However, if 1 and 2 are different colours, it means that no 2 numbers are the same colour. Therefore, no distances between the same coloured numbers can be found. Or put another way, our set D is empty. Meaning on the next iteration, all of the numbers are coloured blue. Now we know what happens when both of our numbers are coloured blue. We iterate the process again because it's a state we've already considered. So we know that the number 1 will be coloured red and number 2 will be coloured blue, but that's also a state we've already seen before. So there's some sort of cyclic pattern here that describes the state space. To visualise this pattern, we can use graph theory. I'm going to assume some basic knowledge of graph theory here, specifically that you've at least heard of it, and the key concepts used to create graphs, such as nodes and edges. Each state will be represented by a node, and each node will have exactly one directed edge, which spawns from that node and terminates at the node that represents the outcome when the process is applied. There's a slight exception to this rule. A target state, namely having every number coloured red, has no edges spawning from it. The process can still be applied to this state, and an edge could be drawn. However, it doesn't need to be, as this goal is to reach this target state, and in this case, we're already there. So we can see, for each initial condition, how applying our process repeatedly will move us around this graph. And in this particular case, where we have only 2 numbers, we'll get stuck in this cycle, bouncing between the state where both numbers are blue and the state where 1 is red while 2 is blue. Let's now have a look at the same process, but with the first 3 integers instead of the first 2. And again, they'll be coloured randomly with a choice of either red or blue. The number of initial conditions will increase by a factor of 2, going from 4 up to 8. This is due to the fact that for each of the previous initial conditions, we have 2 choices, either add a red 3 or a blue 3. We can quickly extend the idea for n numbers. For each, there's a choice of 2 options, either red or blue. Thus, the total number of different permutations is going to be 2 to the n. Now, let's draw the state space graph for the case when we start with 3 integers and look for any similarities or differences between it and its equivalent for 2 integers. Straight away, we can see that we have 3 separate graphs with no edges connecting them. The proper name for this scenario is a disjoint union of graphs. So, whichever graph we start on will be effectively trapped in that graph, unable to ever move to any other graph. However, the graph we start on has no effect on the end result. Just like the previous scenario, we end up stuck in a cycle of states that do not contain our target state. The cycles here are shorter, their length is only 1 compared to a length of 2 for the 2 integers, but that doesn't change the fact that we still get stuck in the cycle. The last difference I want to highlight is easier to spot when we start with 4 integers. Take a look at the spine of the state space graph produced, and by the spine, I mean the subgraph that the rest of the graph feeds into before being trapped in the never-ending cycle. Every state within the spine has its 4 coloured blue. Now, is this a coincidence, or is there some reason behind this similarity? Well, let's think. How would we colour the 4 reds in any of these states? It requires there to be 2 numbers of the same colour, 4 integers apart in the previous state. But we only have 4 integers in every state, so the maximum possible distance between 2 of the integers is 3. The distance between the smallest and largest, i.e. 1 and 4. So there's absolutely no way in which we could ever paint the 4 red in the next state. And the same is true for any finite amount of integers. There will never be a big enough distance to colour in the last integer. So again, there's no way in which the largest number could be coloured red in the subsequent state. So the answer to the question in the finite case is no. We will never reach the target state in a finite number of steps. But how does this transfer to the case with infinite numbers? Well, the problems all arose from the fact that there is a largest number, and that we can never colour it red. But if we have infinite numbers, there is no largest number. So, do all of our problems disappear? Well, let's find out. We can't quite approach the infinite case in the same way. Yes, infinite graphs exist and can be studied, and have many applications, but one thing they're not good at is being visualised. So, instead, we'll look at the state of one number in particular, i.e. what colour it is, and see how that changes as we iterate the process again. The number itself doesn't matter, so we'll just call it y. The colour of y after one iteration depends on 2 points that are a distance of y apart before iterating. Now, what number is y away from y? Well, adding y to y produces 2y, so the distance between y and 2y is y. There are 4 possible permutations of the states y and 2y. Either they're the same colour, or they're opposing colours. In either of the cases where they're the same colour, we know for a fact that there are 2 numbers a distance of y apart that are the same colour. So after iterating, y is guaranteed to be red. However, when y and 2y are different colours, we don't have enough information to tell what colour it will be. So the only way for y to be blue, after iterating, is if y and 2y were originally different colours. This idea can be extended. If we consider the numbers like y, 2y, 3y, 4y, etc., if we want y to be blue after iterating, no 2 consecutive numbers in this list can be the same colour. We can extract another fact from this setup. Consider the number slap bang in the middle of y and 2y, namely 3y on 2. Well, because it bisects y and 2y, it must be the same distance away from each. So, if we want y to be blue after iterating, i.e. y and 2y are different colours, it follows that y on 2 must be red after iterating, because either 3y on 2 is the same colour as y, or it's the same colour as 2y. Again, this idea can be extended. Any distance that bisects 2 different coloured numbers in our list has to be coloured red after iterating. So all the odd multiples of y on 2 are coloured red after iterating, if y is blue after iterating. Now, let's assume this is true, that y ends up blue after iterating, which in turn means that all the odd multiples of y on 2 are coloured red after iterating, and also that all the integer multiples of y alternate in colour before iterating. So, can we figure out this alternating pattern? I.e., does it start with red or start with blue? Well, if 4y is blue, then 2y must be red, because of the first statement. Half of any blue number must be red in any state that isn't the first state. I.e., if 4y is blue, then previously 4y and 8y were different colours, and thus 6y must have had the same colour as one of them, and thus 2y will be red in the next iteration. But if the pattern alternates, 2y and 4y must be the same colour, so 4y must be red, not blue, and thus the pattern starts with y being blue. Now, using again the fact that half of any blue number must be red, and that y and 3y are blue, it follows that y on 2 and 3y on 2 must be red. But now, because y on 2 and 3y on 2 are a distance of y apart, when we iterate, y must be red. But this contradicts our original assumption that y is blue. So our original assumption must have been wrong. Y cannot be blue, it must be red. And as y was any number, it means that all of the numbers must be red, and thus we reach our target state. So the answer is yes. No matter what initial conditions, if we colour all the positive real numbers either red or blue, and then repeatedly recolour the distances between pairs of light coloured numbers red, then we will end up with every number coloured red after a finite number of iterations. And in fact, we can take it one further. Because we only need one iteration to occur for all of the statements to be true, by the second iteration there cannot be any blue numbers. Thus, all the numbers will be coloured red after only 2 iterations.